Today I'm going to talk about several NREC projects that we have going on, and a lot of it's done on Eric Miller's farm. There's a picture of Eric, and there's a picture of our field day last September. There's John Pike giving a erosion/slaking demonstration for us. And so a lot of the research comes from this farm here in Piatt County. But first, let me just say, in general, when we talk about the nutrient loss reduction strategy, Illinois can be simply broken in half, or not quite half, 2/3 and 1/3. And it's because the northern third has been glaciated, it's very flat, needed tile drainage, and therefore tiles carry nitrate, and so we have a nitrate problem in the northern 2/3 of our state. We have less tile in southern Illinois. It's hillier, more overland runoff, and that moves soil and particulate P. So we don't have to worry about phosphorus as much here, but nitrate and tile drainage is what I'm going to focus on. And the source of tile nitrate is a combination of nitrogen fertilizer and soil and mineralization. And I make that point because I'm going to be coming back to soil and mineralization throughout this talk. Now, the industry wants us to know our rights, our 4 rights: the right rate, source, time, and place. I've talked a lot about timing in the past, and I've never seen fall nitrogen application lose less nitrate to the tile than spring nitrogen. In all the years I've looked at tile nitrate, therefore, we know timing does matter. But I want to talk more about the big R, rate. First thing we want to do is get the rate properly set for that year of corn. And what rate should we apply? Well, I think the bigger question is, get it, it's a larger font. The bigger question is how much N will be supplied by the soil in a given year. Now, mollisols have pretty high organic matter, and they mineralize substantial amounts of nitrogen. Our N-rate trials in central Illinois often produce 100 to 150 bushels per acre of corn without any fertilizer. And so apparently I use different numbers than John Jones. We started this experiment a few years ago where we wanted to test or validate the maximum return to N calculation, and apparently fertilizer was a little cheaper and corn was worth a little bit more when we decided that the middle of the range was about 190. I saw John have values more like 170, so maybe we're a little above based on today's prices, but that's what we went with. There's a website if you want to look at that yourself. Now, we've actually done this experiment for 4 years. I'm only going to show you the last 2 years because the first 2 years we put 150 pounds of N on in the fall, and then we came back with 40 pounds or 80 pounds to get to the 190 or 230 as a side dress. Well, that turns out that's a difference in 2 applications versus 1 application. And so I'm not showing that data here. However, we did not see a yield increase of corn with the extra 40 pounds, even when we split like we did. Now, in the last 2 years, I thought, well, we better do apples to apples. And so all the nitrogen is applied at the same time, spring pre-plant. And the extra 40 pounds did not increase yield. You do see we have cover and no cover. We do grow a cover crop out there on half of the plots. It's cereal rye ahead of soybean and winter barley ahead of corn. And we're not growing a very big cover crop out there. The farmer wants to get the corn planted early as possible. I can understand that. And so we haven't grown really enough cover crop to make any significant impact. And so the main point here is that we didn't get any extra yield with 40 pounds. We do have a pretty high plant population, 36,000 plants per acre. Maybe some other things could be tweaked to try and get some benefit out of the extra 40 pounds, but we tried to keep things the same and didn't alter anything else but the nitrogen supply. Now, if you look at the MRTN calculator, you'll see that previous crop matters, and I'm showing this corn plot here to show you how much residue we have in corn. And so there's a large nitrogen immobilization potential with corn residue compared to soybean residue. There's a lot less soybean residue. It's not that the quality is that much different. I think it's the fact that there's 3 times more residue for corn. And so what we see is net mineralization following soybean, and we see tile nitrate go up in the spring in soybean plots that are not fertilized with nitrogen. And we believe that's mineralization. So I've looked at long-term studies, and they do show that we are slowly losing soil nitrogen and carbon with our conventional systems. And I think we're losing mineralized N, especially after soybean. So can we stop, or better yet, reverse the trend of declining soil carbon? Well, to sequester carbon, we have to bank some nitrogen in the soil as well. You can't just add carbon alone. The soil has a ratio of 10 to 1 carbon to nitrogen. That's what it comes to at equilibrium. So it does tend to mineralize. And so we think that if you can add more carbon to the system, we'll tie up nitrate and we'll see less nitrate in the tile. I believe carbon is the key to soil health or soil quality and nutrient retention. So the question that comes out of all this is, can we increase soil carbon and have enough plant available N to still maximize corn yields? Well, when I think of soybean, we used to talk about the soybean N credit. That's really a misnomer. It's not really a credit. It is just a rotation effect. And so I like this idea of bringing winter wheat into the rotation because winter wheat is planted in the fall and it's out there ready to grab that mineralizing N following the soybean. So I think it's a great place to put winter wheat. So it's a corn, soybean, wheat rotation that we have at Eric's. Here's a picture of Eric Miller. I have the picture of him up here to remind myself to thank him every time I have his picture up here, because look what I did to Eric's nice 200-acre field here. We had to isolate these 3 tile systems. And so I put some right angles in the middle of his field, and he has not complained out loud. I talked to Eric into corn, soybean, wheat. We have all 3 phases of the rotation in these 3 fields. In 2014, so that he could get the tiling contractor out there, he grew winter wheat. So we have wheat in 2014. And then 2015, we would have had corn after wheat. We had soy after wheat. And then we had second-year wheat. Starting a study in the middle of ongoing work caused that situation. And so I'm not sure we really thought about it, because I decided that after that winter wheat, that'd be a great place to put a cover crop. And so we planted radish and turnip. So here we are after 2 years of winter wheat. We add all this carbon, but it was proof of concept that cover crops can work very nicely as a nitrogen catch crop. And the annual flow-weighted mean out of that 55-acre field was 0.75. I mean, that is extremely low. I mean, we generally see 8 to 15 part per million coming out of tiles, and many of the samples were below our detection limits. Isn't that right, Corey? Corey Mitchell is our lab worker that feeds me all these tile nitrate numbers, and that's the lowest we've ever seen. Well, maybe we should have had a roadside stand, because after it frosted, we had a very sulfuriferousness event. There's a new word for you. So I heard Shalimar talk about sulfur is important. Well, there is a lot of sulfur in radish and turnip, as much sulfur as there is nitrogen, in fact. And so it's kind of a smelly ordeal after the frost, but that's what it looked like. And Eric puts an NREC trial in wherever the corn phase is. So on one side of the ditch, we have the corn, soybean, wheat, and the other side is conventional corn and soybean. And so after 2 years of wheat and lots of radish and turnip, if you look at the blue dots and look at the 0N, we do have a 20-pound starter on there, so we didn't have a true zero in the beginning, but you could take that back to the line and probably only got 75 bushels per acre with the 0N, where we would have had more like 150 without the cover. So you can see we've got a carbon penalty. Carbon penalty is what I'm going to say. We had too much carbon, so it took us an extra 60 pounds to maximize yield, and we still lost 10 bushels per acre at that maximum. So these triangles, are economic optimum N rates. You heard John Jones talk about that. And just to drive this home, even though this is a post-mortem type analysis, it matches up very nicely with this carbon penalty. You can see at 2,000 part per million over here on the y-axis, that's considered excessive stock nitrate. And the economic optimum N rate was about 150, and it really makes a beautiful post-mortem analysis. Doesn't really help you predict what you're going to do next year, but it lets you know if you put too much nitrogen on, or we didn't have enough. See, we still were deficient under the 750 part per million at 200 pounds with all that carbon. But this is proof of concept. It doesn't take 10 years to change the tile nitrate from your farm. It can be done in 1 year. So that was the first year in this field, and I said, well, that didn't work so good. What do we want to do after wheat in the second year? And we tried red clover. So we frost seeded red clover into the winter wheat, and it worked extremely well. This is one of the last times I sat on the ground. It's getting harder to get up all the time. And so that was a lot of red clover. That was like, I believe, 3 tons, and it had over 100 pounds of nitrogen in it. I'm thinking this is going to be a great way to get nitrogen into the next corn crop. And the end credit was less than 20 pounds. We had a 20-pound starter out there, and I couldn't see any end credit, in fact. It's like, well, where did all that nitrogen go? Some of it did get in the tile, but that was just a small amount. Now, the tile nitrate concentration did go up after we had red clover out there, but it didn't explain where'd the 100 pounds go. So in 2018, in that same field, we had the best soybean crop that I've ever seen, 97 bushels per acre. That 75-acre field had 97 bushels per acre. And in the conventional side, which gets full with tillage, no cover crops, had 86 bushels per acre. Well, that's a fantastic yield. But to see 11 bushels per acre more out of the soybean, and we didn't fertilize it, but this is a year after all that red clover. So was this a delay in the end credit? Did it manifest 1 year later? I guess it did. Now, why? Well, I was at a small grains conference back in 2020, and I was presenting this information to organic farmers, and they said, well, did you till your red clover in? And I said, no, we didn't. He goes, well, if it just laid on the top of the soil, you may very well have just had a delayed end release. I go, wow, I should have thought of that myself. Thank you. So there was a farmer's wisdom giving me some explanation of what's going on, and I think that's what happened here. So Eric has a yield monitor. He was seeing 110 bushel per acre in areas of that field. That's a tremendous yield. So is there something to organic N released from red clover that the soybean likes? Well, I think it's getting ammonium and not nitrate, and ammonium is a benefit to the plants because it's already reduced. Oh, there's a picture of Eric again. That's because Eric came up with the real solution. Year 3, Eric says, why don't we grow double crop soybean after the wheat so I can get some of my money back? And I said, well, that's a real good idea. So in this top field here, we had done everything right by accident. We started with wheat in 2014, then we went to corn. Then we grew cereal rye after the corn, ahead of the soybean, then it's winter wheat and double crop soybean, and we repeated that for 2 more times through the rotation. So we had 9 years of data on this 175-acre field, and we compared it to these 2 conventional corn-soy fields to see what type of nitrate reduction we get out of the tiles between those 2 systems. And here is Eric's double crop soybean from last year coming up through the winter wheat residue. So from that point on, we've had the systems comparison, conventional full width tillage versus strip-till corn, no-till soybean, no-till winter wheat, and no-till double crop soybean. And we published that last year. It wasn't just me working on this. It's Corey and John and Carlos, Eric and Dan Schaefer on the paper, and Annette and Dr. Yu. And so here is the 8 years of conventional tile nitrate data. And just to put an average across that, all those dots, the flow-weighted mean nitrate concentration for those 8 years is 8 part per million. And let me just reference the drinking water standard of 10 part per million and say that this data set, 35% of the samples were greater than 10 part per million and 15% were less than 5. And you can see some really high values. We got up almost to 20 part per million in June of 2019, and at the same time, the cereal rye was down to 1 part per million. So we can have that much impact on tile nitrate just from one side of the ditch to the other, same soil type. But now we're looking at 9 years of data. So my one single field to get through the rotation 3 times, 3-year rotation, took 9 years. And we did start the conventional 1 year later. So anyway, this is the 9-year average, and it's 4 part per million. So we were able to reduce tile nitrate by about 50%. This is the signature of the samples that have tile nitrate, that have nitrate in them, from the cereal rye. So you can see the cereal rye does a great job of bringing tile nitrate down the 3 times it's in the rotation. Very nice. This is the biomass that we had, quite a range. We found over time you need at least about 1/2 ton to reduce the tile nitrate significantly. But 2.65 tons per acre, that's more than we needed. We actually had a small yield hit. Well, it's not that small. 8 bushel per acre loss of soybean yield with that much cereal rye. So there's our range. You don't need to go over 2.5 tons per acre, I say. But you can see how much nitrogen's in it. This 0.77, 43 divided by 0.77, that's the seed-N ratio. It'd be about 56 to 1. So it's quite recalcitrant when it gets that big as well. So here is how well winter wheat does on the tile nitrate for the 3 years that we had winter wheat. You can't tell much difference from cereal rye. And yet we're putting 120 pounds per acre of nitrogen on winter wheat, yet it is that efficient. So winter wheat's acting like a fertilized cover crop, doing very well. I'd like to show this a little out of sequence, but it's from Eric's farm and also the Douglas County farm where we had a replicated tile drainage study. And if I just look at the amount of cereal rye biomass compared to the amount of tile nitrate loss reduction in percentage, that we have a pretty good R squared, probably thanks to these 2 times Eric planted green to set that regression a little higher R squared. But nonetheless, it looks like it takes about 1.5 tons of above ground cereal rye biomass to achieve our goal of 45% reduction. This is what 1/2 ton looks like. That's about what you should aim for. If it's strip till, well then you need a little bit more because you're reducing about 1/3 of your cereal rye when you strip through it. Now, you don't have to do this. This is Eric planting green. This would have been better if we roller crimped it too, so maybe some of the loss to the soybean yield was just in self-shading. Now I want to talk about 10 years of NREC trials that NREC puts in for us. As I said earlier, we didn't have a true zero in the first few years, but now we have 0, 50, 100, 150, 200, and 250. Calculate the economic optimum N rate. Emerson Navsiger has calculated that for me. Thank you, Emerson. John Jones recalculated, and they're the same value. I was happy to see that. So well done, you guys. And so I want to compare the differences based on weather. Same soil type, same farm, but a tale of 2 years is the difference between 2017 and 2018. 2017 is such a warm winter. Great year for cover crop, terrible year for fall end, by the way. But 2018 is the reverse. And the month I really want you to look at is April. I think April is really important for setting the stage for how much mineralization you have and maybe how much nitrogen fertilizer you need. So in 2017, we had a very high April average temperature. The middle bars are the 30-year average, by the way. And the green bars then is the 2018, and you can see how cold it was in 2018. And then the reverse of in May, where it got really hot and the corn just jumped out of the ground. But nonetheless, I'm pointing out the difference in April temperatures. So the economic optimum N rate that year is the lowest we've seen in the 10 years until this year, and I'll explain that. But 144 pounds per acre maximized yield in that warm year. In 2018, with the cold April and a very excellent grain fill period, which will probably add complexity to that simple idea that look at the April temperatures, but nonetheless, we needed almost 200 pounds per acre to maximize yield in 2018. And so a summary of that would be that when you have a warm spring, you have greater mineralization, your economic optimum N rate is lower, and your delta yield, or the bang for buck, the change in yield with your nitrogen fertilizer application, also goes down. Cold spring is the reverse. Cold spring, lower mineralization, higher economic optimum N rate, and more responsive corn crop to the fertilizer. Well, I said that that was the lowest we'd seen up until last year, and now we matched that. In 2025, we only needed 144 pounds in our conventional system after soybean, and we reached 254 bushels per acre. It's a very excellent yield. But in our 3-year rotation, where we're following wheat, double crop, soybean, we only needed 132 pounds per acre, and our yield level was higher. I'm going to say I think this is an example of sustainable intensification. We've got 4 crops in 3 years, and we're increasing our yields, and we are minimizing nutrient loss. But I also wanted to show that the 0N yield of corn was very high, 150 bushels per acre, in both the 3-year rotation and the 2-year rotation. And that can be explained by a year of high net mineralization. And we see from this map here from Iowa State that it's pretty much a bullseye over central Illinois for the most or the highest rate of mineralization. And so this was a year that had warm temperatures that in April that created quite a bit of mineralization. And so that explains why the 0N corn plots were very high this year. But what explains the fact that we required 12 pounds per acre of less nitrogen to produce 10 bushels per acre more in 2025? And I think that can be explained with this visual representation or visual look at what NREC's strip till looks like. You can see lots of residue, lots of cover, keeping the soil temperature lower. And then you see in conventional tillage, you see that it's largely uncovered. Well, that may explain part of the difference in why the diverse rotation out-yielded the conventional rotation. And I want to bring your attention to NREC videos, one that I had done back in 2024, all about Eric Miller's farm, and that's entitled Benefits of Reduced Tillage and Cereal Rye in a Diverse Crop Rotation. You can find it there on YouTube, and you can see lots of images of how many worm middens are present in the 3-year rotation. A midden is a worm home. It's their hole. They're dragging carbon down into the soil. But I really want you to look at the 7:30 minute mark, in case you can't sit through the whole 8-minute presentation. At 7:30, you can see me pick up some dry, crumbly soil from the conventionally tilled plots. And this was for B-roll, and we filmed this on April 15th. And the very next day, afternoon of April 16th, parts of Interstate 55 and 74 were shut down due to blowing topsoil. And so I think we captured just what conditions were ripe for a windy day, unfortunately, in conventional till. So I got to bring us back to think that, yes, these are great. Economic optimum N rates, very low, means there was a lot of nitrogen available. But we put 180 pounds per acre of nitrogen fertilizer on each field. So what happens to the additional N, or the amount of N that's greater than the EONR? And that would be 36 pounds per acre in the 2-year rotation, and an extra 48 pounds that wasn't needed in the diverse rotation. Well, I think the fate of this extra N may be very different between the 2 years, and I take you back to those pictures that we just looked at with the wheat residue and the benefits in the diverse rotation. That nitrogen probably is going to be captured by the cereal rye that follows the corn, and so I think the diverse rotation might allow us to sequester carbon because we're banking some of that fertilizer nitrogen as organic N. Where in conventional, there's no living roots out there in the non-growing season, so that nitrogen that is in this extra category could potentially leach to the tiles. So in closing, I just want to say that again, mineralization of soil organic matter is an important source of tile nitrate, especially during the non-growing season following soybean production. The diverse crop rotation with winter wheat and cereal rye after corn captures mineralized N and reduces tile nitrate loss. We saw a 50% reduction in tile nitrate loss over a 10-year period compared to the conventional plots. So, to sum it all up, tile nitrate is not simply a matter of excessive N fertilization. It's much more complicated than that, and it's clear that mineralization plays an important role in not only crop production, but in the off-season it can generate and liberate nitrogen that can ultimately move to tiles, and we want to try and close the system as best we can. We know we have a few leaks in the system, and one of them is following soybean. And winter wheat is an excellent choice after soybean. But in front of corn, it's difficult to come up with a cover crop that works every time. We've been trying winter barley in front of corn. But cereal rye in front of soybean is almost a no-brainer in my mind as far as trying to keep the soil covered and keep our mineralized N out of the tiles. Thank you.